Meta just dropped a new AI model that's honestly pretty fascinating. It's called VL-JEPA, and I think it represents a genuinely different approach to how AI systems process information. Not just another incremental update. This feels like a fundamental rethinking of the whole setup. Here's what's interesting. Every major AI you've probably used, GPT, Claude, Gemini, they all work the same way under the hood. You give them an image, ask a question, and they generate text, word by word, token by token, until they've constructed an answer. That's literally how they're designed and trained. But VL-JEPA, which stands for Vision Language Joint Embedding Predictive Architecture, takes a completely different route. Instead of predicting words, it predicts meaning directly. And once you understand why that distinction matters, it becomes clear we've maybe been approaching this problem in a complicated way. Let me give you an example. Show a standard model a picture of someone flipping a light switch and ask what happens next. A person might say, the light turns off, or the room goes dark, or the lamp stops working. All correct answers that mean essentially the same thing. But to a language model, those are three entirely different responses. Different words, different token sequences, virtually no overlap. So during training, the model burns through massive computational resources, learning every possible way humans might phrase the exact same concept. It's memorizing linguistic variations when all it really needs is to grasp the underlying idea. That's the first major inefficiency. The second issue is speed. When you're generating text one token at a time, you literally can't know what the model is trying to communicate until it finishes the entire sentence. For applications like smart glasses or robotics that need real-time responses, that delay becomes a critical limitation. You're just waiting for the model to complete its thought before you can even begin to process what it means. VL-JEPA sidesteps both problems by eliminating the text generation step during most of its operation. Instead of predicting the next word, it predicts what the answer should mean, represented as a continuous vector in what's called embedding space. Think about it this way. In traditional models, the light turns off and the room goes dark are treated as vastly different because they're different symbol sequences. But in embedding space, those answers can exist right next to each other because they carry the same meaning. That's the core insight. By operating in meaning space rather than word space, you transform a messy, multi-option problem into something much cleaner and more learnable. The system has four main components. First, a vision encoder processes your image or video into visual embeddings. Then the predictor, the system's brain, analyzes those visual embeddings, reads your query, and predicts what the answer embedding should look like. There's also a Y encoder, which during training converts the correct answer into an embedding, so the model has a target to aim for. Finally, there's a Y decoder, but here's what's clever. It barely gets used. It only activates when you actually need human-readable text at the end. Most of the time, the model just operates in embedding space and never touches language at all. The performance gains are substantial. They ran a controlled comparison where everything was identical. Same vision encoder, same data, same training steps. The only variable was whether the model predicted tokens or embeddings. The token-based model used about 1 billion parameters. VL-JEPA used half that. Yet, after 5 million training samples, VL-JEPA was nearly twice as effective at video captioning. It learned faster, scaled better, and continued improving where the baseline plateaued. That's not a tuning trick. That's a fundamental architectural advantage. But the real breakthrough comes during inference, especially with video, because VL-JEPA outputs a continuous stream of meaning. It can use what's called selective decoding. Instead of generating text every single second, it monitors the embedding stream and only decodes when something semantically significant changes. In practice, this reduces decoding operations by nearly 3 times without sacrificing accuracy. For real-time applications, wearables, robots, anything that needs continuous environmental understanding, that's transformative, and it's remarkably versatile. The same model handles classification, retrieval, even world modeling tasks where it determines which action caused a change between 2 images. In that test, it outperformed GPT-4, Claude, and Gemini, all of which attempted to solve the problem by first describing what they observed in words. Turns out, predicting meaning directly can be more effective than narrating everything and reasoning over the text afterward. Now, this isn't going to replace language models across the board. If you need complex reasoning, sophisticated planning, or tool use, you still want a token-based system. But for perception-heavy tasks, particularly anything involving video or real-time understanding, this approach just makes more intuitive sense. It's faster, cleaner, and more efficient. Most importantly, it shifts AI away from pure word prediction towards something closer to how humans actually process information. Meaning comes first, and language is simply one way to express it. And honestly, that feels like the beginning of something genuinely new. Thanks for watching, and I'll see you in the next one.